Hi again. In this video, we'll do an example to practice a theoretical sampling distribution. So I've got my whole page that has all the conditions and both formulas on here. Okay, so this is our, I believe, second page of this particular group of videos. So I've got that handy. We'll refer to that. And then what we're going to do is we have a situation. We're going to write about the conditions to make sure that our model will apply. Then we're going to define, draw, and label our model, just like we did before with the normal distribution. Then we'll use it to find some probabilities and answer some questions. That's kind of the general gist of how these questions will go. Okay, so let's read about our situation. We have information on a packet of seeds claims that the germination rate is 92%. Okay, so we have a P or a P hat, right? We have a P hat. This is like one packet of seeds is like our sample. There are approximately 160 seeds in each packet. Okay, so I'm going to write that's our N. Okay, so we have an N and a P, or in this case, P hat. Or I guess we could call this a P. It's kind of tricky sometimes to know which, if it's P or P hat. I'm going to say this is a P. Might change my mind later. So I'll be a little, I'll be gentle on that as far as grading. Write about each of the conditions in context. Required to use a sampling distribution for the proportion of seeds that will germinate or will sprout. Okay, have you ever planted seeds and some of them come up, some of them don't? And different types of plants and seeds have different germination rates, and of course how they're stored and all processed and all that makes a big difference. Okay, so write about our conditions. So first of all, I'm going to look at my notes real quick. So these first three apply to both means and proportions. And then we do have a proportion here. So then I'm going to go down to the second number 4 and look at the success failure condition. Okay, I'm just going to keep this off to the side. Hopefully you can refer to yours as well. Okay, so the first condition is independence, and we're going to write a fair amount here. So I'm going to leave a lot of space. Independence, number 1. Okay, now we won't always be given a lot of information about this, but I want to specify what we would need. Okay, we are going to take a random sample, or say we need a random sample. But if we were doing this in real life, we would be doing this hopefully before we take our sample. So we would be thinking about, okay, what do we need for independence? What do we need for large sample size? What do we need for random sample? Okay, so for independence, the seeds must be independent from each other in terms of germination rate, right? So the seeds must be independent from each other in terms of our variable, which in this case is the germination rate. Okay, so what might we need for that? We would need seeds from different plants, right? Now, we don't know if this is like all tomato seeds or if it's like mixed flowers. So, of course, if they were different types of plants, that would probably help as well. Okay, I'm just going to say, the seeds should be from different plants to be independent, but that may or may not be happening. But ideally, I'm going to list out what are our ideal conditions. Okay, so then for number 2 is randomization. Okay, the seeds must be a random sample, right? We need a random sample. So I kind of have a question here. Is a packet of seeds, when you buy a little packet at the store, is that a random sample? Is a packet of seeds a random And for that, I don't know. And it probably depends on the seed company and how they're processed. Do they take all the seeds and dump them in a bin, and are they mixed really well and then they put them in the packets? Or is it like, okay, this one from this tomato goes in here, and this tomato goes in here, this tomato goes in here? So I don't know, but ideally it should be, right? So ideally it should be. Okay. Okay, so if we're setting up our thing, we would want to take a random sample of seeds. Maybe we take a few packets, we mix them together, and we take a random sample, or we take some out of each packet, or something like that. Okay, so lots of things to consider. Okay, so now third is the large population. Remember, this is the small bag of M&Ms versus big bag of M&Ms. We need to make sure, I'm going to say it like this, we need to make sure our population is at least 10 times the size of our sample. And so if we have 160 seeds, we need at least 10 times, our population of seeds must be at least 10 times that. Okay, so we can, for that we add a 0, and it would have to be 1,600 seeds. Okay, the population must be at least 10 times our sample. So at least, I'll write it out, 160 times 10 is 1,600 seeds. Okay, and of course your wording doesn't have to be exactly the same as mine. Just get the general idea. And you might think of some things in terms of independence and randomization that I don't think of, so that would be great. Okay, so now we are to our fourth condition, and that one for a proportion is success failure. So I'm going to write this out so you can see how to do it. N times P and N times Q have to be at least 10. Now notice that's a different 10 than this large population 10. It's just kind of a coincidence that they're both 10. Okay, so 4 is success failure. And remember that wording, I think, is kind of unfortunate. It's the thing we're looking for, right, is a success, and the opposite of that is a failure. So I'm going to write N times P, and then I'm going to plug in my numbers. So my N is 160. And our P is 0.92. So we're always going to turn our P into a proportion, a decimal. Now I need to calculate this, and this needs to be at least the number 10. 160 times 0.92, 147.2. So no problem. That is greater than or equal to 10, so I'll put a check mark right there. And then N times Q, so I just want to remind you that Q is 1 minus P. So if this is 92%, what's left to make up 100 is 8%. So you can go ahead and keep it at writing 1 minus P if you'd like, or you can go ahead and calculate it in advance. It's up to you how you want to write it out, as long as you show your steps. And I'm getting short on space here, so I'm going to figure out how to write it. So N times Q, so I think I'm going to go over here and write 1 minus 0.92 equals 0.08. I could write it over here, I just don't have enough space right now. So NQ is 160 times 0.08. I know I did it to myself by not spacing this out well enough. So 160 times 0.08. This is the smaller one, so this is actually the one we're concerned about, right? But we just check both directions. 12.8. Okay, so just barely. 12.8 is greater than or equal to 10, so I'll check that off as well. Okay, so that's how we check our success failure condition. We find our Q, 1 minus P, and we test N times P and also N times Q. Okay, Now, these should all meet. If for some reason you come across one that doesn't, we're still going to do the question. It's not like I'm going to trick you and say, oh, you shouldn't have done this because we didn't meet the conditions. Okay, so we're still going to do the question, but they should all be set up to meet the conditions, even if just barely, like this one. Okay, so now we get to our model. We're getting to I know that the conditions are kind of tedious, but they are really important. That's part of statistical thinking, right? It's like we've got a model. What are the conditions we need to apply this model? And if we're using it when the conditions don't apply, then we're not doing ourselves any favors, right? We're not doing a service. We're doing a disservice. Okay, so here's our actual model. P hat is distributed, so it's going to be the distribution of sample proportions. It follows a normal, if these conditions are met, it follows a normal model with a mean of P and a standard error of square root PQ over N. Okay, so I'm going to define that. That's why this definition statement is so important, because we need to define what model we're using. Okay, so the define part is this. Our distribution of sample proportions, I'm going to go ahead and write out the formula here. Our distribution of sample proportions is distributed as normal with a mean of P and a standard error or standard deviation of square root PQ over N. Okay, and now I'm going to plug in my numbers. And so that's why I changed this to P up here, because so this is kind of claiming this is the population. So that's why I took the P hat off of there. We don't have a sample proportion just yet, so we will in a bit. Okay, so to rewrite this with the numbers in here, P hat is distributed as normal with a mean of 0.92, and our standard deviation will be the square root of 0.92. We've already calculated our Q, so once you do that, you can keep using it. 0.08 over 160, which is our N. Okay, so I'm going to calculate this. We're going to use this to draw our model, or we can put it in to Staplet, either one, now that you've been practiced at using the normal model. Okay, so I'm going to put in square root 0.92 times 0.08 divided by 160. I can do this all in a row because multiplication and division go left to right, and it's all under the square root symbol. Now I'm going to keep 4 decimal places to put this in Staplet, okay, to keep it very accurate. So 0, 2, 1, 4, and then a 4. So 0.0214. Just going to write it underneath there. You could, if you want to calculate on the side and put it in there, that's totally fine. Okay, so I'm going to draw this by hand and show it to you on Staplet in case you might be doing it either way. So for my drawing, I'm not going to go all 4 decimal places. I'm going to go 0.02 for my drawing. And that'll be close enough. Okay, so I'm going to make my normal curve over here, like that. And then I wish I had left myself a little more space, so I'm going to get rid of that line for 1 second real quick. Okay, the magic of the pause button. I realized I needed to leave myself space to label the distribution underneath. Okay, so this is, now that we've got our mean and standard deviation, it's just like we were doing last time with a normal model, right? We always put our mean in the middle, so that's 0.92. And we divide each side into thirds. 1, 2, 3, with about where it comes down. 1, 2, 3. And your drawing won't be perfect. You can see mine's not perfect. Okay, and then I could use the whole 0, 2, 1, 4. That's what I'm going to put into an app. But for my drawing, I think it's just more understandable if I go by just 0.02. So we have 92% to 94%, 0.94, 0.96, 0.98. And then we're going down to the left. Let me scoot this up a little bit. That would be 90, 0.90, 0.88, 0.86. Okay, so that is approximate, right? But that's okay. We'll be getting our probabilities from Staplet anyways. Okay, and now I want to label, what is this? Okay, so these are sample proportions, right? So I want to label that, and I want to talk about, this is the numbers, that's what we're labeling, this scale, right? This is the proportion of seeds that germinate in samples, so per packet, in samples of 160. Okay, so I'm going to write that out. Proportion of seeds that germinate or sprout in samples of 160. Now, why am I putting 160 in my title and my label and my graph? Well, what would happen if there were only 100 seeds in a packet, or if it was a jumbo 500 seed packet? This distribution depends on n, right? That would change the standard deviation. So I would have a narrower graph or a wider graph. So if I just put proportion of seeds that germinate, standard deviation could be anything, right? But this is specific to packets of 160 seeds. Okay, so let's go ahead and put that into Staplet, because now we have a question. It says, what's the probability that more than 95% of the seeds in a packet will germinate? So let's see, I've got to find my Staplet first. I think I have, yeah, I'm still on one proportion here. There we go. Here's my Staplet, and if you're on staplet.com, it's the first one under probability is normal distributions. So the beauty of this is we can just use the normal from here on out, right? As long as the conditions are met. We're going to be finding a probability, so that is an area. And I'm going to put in our mean of 0.92 and our standard deviation of 0.0214. And plot distribution. So if you were hand drawing this, you could also use these numbers right here. That's fine if you want to do that. I just wanted to show you more by hand method, and then this, or you can also, if you're typing, you can copy and paste or do a screenshot of this distribution here, and then type your label underneath. Okay, so there's our model. It should be roughly 92, 94, 96, 98. You can see if you round it, it's accurate, and this would be 90, 88, 86. So it's not too bad, rounded off. Okay, so now we always want to find a probability. Like we'll be thinking ahead, we'll be getting a p-value, right? Here we want to know, what's the probability that more than 95% of the seeds in a packet will germinate? So what's the probability? Now we're talking about p hat, because remember, these are all samples of p hat. So what's the probability that p hat is more than 0.95? Okay, and if you want, you can draw it in your on your diagram. So I'm going to go 0.95 is halfway between 94 and 96. That's the area that I'm looking for. And so now under calculate the area, I want to choose to the right because it's more than, and put in 0.95. Okay, notice our scale is a percentage. Sometimes this gets confused with the inverse normal when you're given, because we're dealing in percentages here. Our scale is a percentage, but we're still finding a probability. So if you're finding a probability, you're calculating an area, even though you're putting in 0.95. Okay, I'll show my labels. Our probability is 0.0805, and that probability corresponds to, looks just like what I shaded on the paper. Okay, so 0.0805. Okay, and then remember, if it asks for a percentage, you could put in 8.05%, depending on how the format that the question is looking for. Okay. Okay, so before we did this in a sampling distribution, remember? And we would, each sample would be a dot on our dot plot. And then it would form, we do about 2,000 samples, it would form usually a normal shaped curve. And then we would count the dots, right? How many samples were over 95% that would germinate? So this is very similar, but now instead of counting those dots from a simulation, that's an empirical probability. This is a theoretical probability. We're using this model under the conditions, if the conditions are met, and we can use that model to find our probabilities. Pretty cool, huh? Okay, so let's answer the next question. If you buy a packet of these seeds, would it be unusual for only 140 or fewer of the 160 seeds to germinate? Okay, so let's say you've got a packet of these seeds and you're like, should I take this back? Should I call the manager or whatever? Is this unusual? Okay, if you buy a packet of these seeds, would it be unusual for only 140 or fewer of the 160 to germinate? So notice how we were given a percentage right here, and here we're given two numbers, so we're going to divide those. We have to find this p hat. P hat is 140 over 160. I think I'd call the manager over a packet of seeds. That's kind of a joke. Okay. It's a Karen joke. Okay, 140 over 160 is 0.875. Okay, and then we also have a direction, 140 or fewer, right? So this probability is going to be, what's the probability that p hat is less than 0.875? Okay, now let me put that on my graph, A687, that would be right about here. Okay, doesn't look too bad. Let's see what it is in the actual app. So this time we're going to go to the left of a value 0.875. Okay, and this is 0.0177, so pretty small. And we could also look at the z-score, right? That tells us too, because we know that more than 2 and especially more than 3 is really unusual. So our z-score it's over 2 below the mean. So I'm going to write that too. Our z-score equals negative 2.1 standard deviations. Okay, so let's go back to our notes where I wrote that down. So I wrote down the probability that p hat is less than 0.875 is 0.0177. So that's pretty small, right? 1 to 2%. And we're over 2 standard deviations from the mean. So we're definitely outside of that middle 95%, right? So it seems like it would be unusual. And so maybe something is off with these seeds, or maybe something's off with the advertising of the rate that's on their packet, okay? So I'm going to write, it would be unusual for only 140 out of 160 seeds. To germinate if the true, this might remind you of hypothesis testing, if the true germination rate is 92%. Okay, so something is off, and we could say it's, we could explain further that it's more than 2 standard deviations from the mean, or it's a very small probability. Okay, so that gives you a whole sampling distribution example for for a proportion, and we will look at another example in the next video. So I'll see you there.